This video tutorial is to show how to set up an I-beam in ADAPT-PT 2015. This also applies to ADAPT-RC 2015. We're in the ADAPT-PT 2015 interface. We're going to go to File and select New. And we're going to go into the general settings of the program. So in the general settings tab, we're going to select the option for a beam. And in order to activate the I-beam, we're going to select the option for no for effective width consideration. So this only applies to a flanged T-beam. We'll select no. We're going to use conventional input as compared to segmental. And we're going to use the design code ACI 318-2011. Under the design settings, we will use all of the settings shown as is under the default condition. And now we'll get into the span geometry. So in the span geometry, under the section type, we're going to do a one span I-beam, and we could do multiple spans if needed, but in this case we'll do just a one span, and it will be a simply supported beam. Under the section type, we're going to select the section, and we're going to do an I/L section. And now we get additional input parameters which are now active, allowing us to set up the geometry. So for the length of the span, we're going to say this length is 45 feet. The dimension parameters are illustrated in the sketches above the input table. So for an I and an L section, we're using this third sketch to reference from. The B dimension is going to be the dimension of the web. So for this dimension, we're going to say this is 12 inches. The total height of the I-beam we'll say is 36. The top flange for the beam will be 48 inches. The H sub F is the thickness of the flange, and for the thickness we're going to use 5. The B sub M value is the bottom flange width. We'll use 48 again. And then the bottom flange thickness again is 5. So this is a symmetrical section. As we develop that section in the structural view, we can see the beam produced. I can also just rotate that around just to make sure it looks correct. If I go to a front view, we have a front side view, and go back to a top view, and again we can rotate that just to see the section. So this is our beam that we're developing. The reference height, I typically will recommend to set the reference height equal to the depth of the structure, the depth of the beam. This allows us to have positive values for the CG of the beam versus negative, since they are referenced from the reference plane. So we're going to set this equal to 48 inches. And then the multipliers left and right, those are the multipliers for the top flange to the left and right sides of, the reference height should be 36. The multipliers just reference or allocate the distribution of the top flange to either side of this datum. So the left side would be on the top, the right side would be on the bottom, and the flange can shift between those two. So we'll go ahead and say next. In the next input window, we can set up our support geometry. Again, in this case, we're going to assume that this is a simply supported beam, so we'll have pins on both ends. We have no columns. We could set up columns lower or both top and bottom, input the height and the dimensions of the column in this window. The support conditions will be set here. So for the support width, this is going to be set to 0. We're not reducing moments to face of support by default. If we wanted to bring back the design to a specific face of a support, for example, we could input a dimension here, and the program would interpolate and give us the design based on a distance from this support center line. In this case, we'll just use 0. We'll now go ahead and enter some loading. We're going to turn off the skip live loading, and this will be for span 1. We'll just put a dead load and a live load on the structure. We'll use line loads. So the dead line load we're going to say is 4 kips per foot. The live load we'll say is 6 kips per foot. And by default, the distribution is over the full length of the span. We could enter additional loading types that are shown here in the loading table. For the strength, we'll use 5,000 psi concrete. Make sure when you change the strength, you press enter for that value to update. And then at the concrete stressing, we're going to assume 3,000 psi at the time of stressing. We'll use the defaults for material assignments, and we're going to assume that this is an unbonded system with the different parameters shown here. We're going to use 1/2 inch diameter cables, assuming an effective stress of 175 KSI. There will be no base reinforcement in the beam. We're going to assume it's just a bare concrete section, and we'll allow the program to calculate the reinforcement for us. We can change the allowable tensile and compressive stress values. So for tension, we're going to use 7.5 for sustained and total. And for initial, we'll use the 3. This is at the time of stressing. The program will check against that initial stress allowable. For the average precompression and the percentage of dead load to balance, we can set the ranges for those design parameters. So for dead load balancing, we'll say 50 to 100%. We'll leave the average precompression as is. And in this design, we're going to use the force selection method. A lot of times for I-beams, these are actually pre-stressed girders, and you would want to reduce or eliminate the active nature of the friction loss and the seating loss in some cases. So to do that, we would either have to go back and adjust our value for the effective stress input, which is shown here. This is assuming we do have friction loss and seating loss plus the long-term loss. So we might increase that to put back in the friction and seating, or we could go back into the pre-stressing calculation type, and we could set this to calculate force, number of tendons, and in this entry we can modify and set the parameters required for a real pre-stress type of a condition. In this case, we're assuming that this is cast in place, and we're designing it as such. So we're going to go back and just use force selection method. We can adjust the shape of the cable. So for this cable, we're not going to use a reverse parabolic shape. I want to use just a simple parabola, and you can see we have inflection points at x1 over L and x3 over L at 1/10 of the span from either end. To make this a simple parabola, we'll just set these to 0, and we're only going to be using tendon A for this particular case. So we'll go next. We can set our cover requirements. So for the CGs, we're going to use 2.5 for the PT, and for reinforcing, we'll use 2 inches. We have bar extension criteria, and these are just minimum lengths for the bars. These are more relative to a two-way slab, a pre-stress or post-tension slab. So we're more focused on these bar extensions here for strength. We'll just leave those as 12 inches. We could set up curtailment rules for the bars using this table, but we're going to go ahead and turn that to none and off. We're only going to use the minimum bar extensions and not customize the output of rebar. And then we have load combinations. So we're checking 2 strength combos in this case, and then we're checking service level stresses and forces at a sustained condition where we include 1/3 of the live load plus the dead load, and also a total service condition where we apply all of the load. We also consider the initial condition where we stress the cables. So we'll go ahead and say OK, and we're going to save the model. So once we've saved the file, we're now going to execute. So we can go to this execute tab, or we can just select execute here, and the program will run through the design of the beam. Once it's selected the post-tensioning for the beam, we can see the program has opened up into this PT recycling window, and this allows us to review the results of the beam. So it shows an upper left block where it's just checking the different serviceability requirements, and it's either no good or okay. For PT force, this is just the pre-compression range that we entered, which was 125 to 300. The balance loading range between 50% and 100. So here you can see the design does not satisfy the balance loading range. The balance loading is actually 10%, not 50. So in some cases, the program cannot have an acceptable solution or obtain an acceptable solution for each of the different criteria. So it goes through multiple iterations and then it stops that iterative process and it reports back to you where it stopped, and this is the condition where it stopped. So it meets the pre-compression. That's kind of the fundamental basis of design that the program meets. And if it can't meet balance loading or stress conditions, it would then come back and report back, no good in this case for the balance loading and also for the stresses. And we can see the force right here, 99 kips, is actually required for P over A. So the program couldn't find an acceptable solution to meet all three, and it goes back and it reports back only the force required for P over A. If we look at the required force for stress allowance, it's 1163 kips. And so if I go back to the input and I change this to 1163, and then it asks us to recycle, we'll go ahead and recycle that and update the design. Now we have a situation where we're overbalanced for the balance loading. The pre-compression is very, very high. The stresses are okay tension-wise, but compression-wise they're not okay. And then the initial stress is no good. So in this process, this example, we have just too much load on this beam. The beam's not deep enough. We don't have the right section to actually design this and obtain an acceptable design. But assuming that we have an acceptable design, once we exit the recycling screen, the program will go through some post-processing of deflections and reinforcement output, and we go into this mode of the wizard where we get into the shell. So this shows us just general results. If I go into the graphical solution, this will show us bending moments, shear diagrams, deflections for the beam, stresses, and so on. And those are just the raw results from the analysis run after we've selected the post-tension in the beam. We can also activate the report generator in this window. So this report generator allows us to select any of the reports on the left and include them in a report that we can then create in a Word document. We can also go into this yellow tab, which is called Builder Sum, and this is the summary of results from the load combination standpoint. So here we're selecting the envelope of results. If I was to generate a summary report for the envelope, the program will show me the member elevation, top and bottom reinforcement, and just give a summary of the flexural requirements versus provided and the shear requirements versus provided, and then output some design parameters and material quantities at the bottom. So this is a nice summary sheet to just gather all of the information in a condensed format to be able to present in a calculation package or just to review the design for the user. We can also produce this for any of the load combinations. So we had 2 service combinations, we had a couple of strength combos, and then the initial combination. And if we, for example, select strength 1, maximum live load, this shows us the reinforcement requirement for that particular combo. So we need 19 number 5 bars and 27 number 5 bars in the bottom. So this requires quite a bit of reinforcing. And again, we can do the same from a strength standpoint, or I'm sorry, a serviceability standpoint, or minimum rebar. If we go back into Builder Sum, the last thing we'll show is the DXF. Once we've studied the results and made sure those results are acceptable, we can go to DXF and we can create a drawing of this particular beam design. So if we select Create DXF, the program will open that file in AutoCAD, and it's going to produce all of the post-tensioning information, the longitudinal reinforcement and also the shear reinforcement in a CAD file that can then be used in your drawing set or just used to relay the information in some other format. So we have, again, a schematic of the beam. On the top, we show the post-tensioning information, and then we have longitudinal reinforcing information and shear stirrups shown here. And these vertically, we've actually scaled this by a factor of 5. That's why the beam looks taller than it really is. But we can set that scale when we generate the DXF. If you have any questions about modeling an I-beam in the program, please contact ADAPT support, and that's support@adaptsoft.com. Thank you.